All right, let's try out our first problem. It says, if we have enough of everything else, how many pancakes will 8 eggs make? So they give us one value to start with. So I'm going to write it here. I have 8 eggs. And our reaction is right here. It's a recipe. So what we're worried about is for every 2 eggs that we react, we're going to make 5 pancakes. So the coefficients that we're focused on are the 2 and the 5. So I'm going to use those like a conversion factor. I'm going to put eggs on the bottom so that my eggs cancel. And I'm going to put my pancakes on top. And then I get my ratio from the coefficients. So the recipe called for 2 eggs for every 5 pancakes. So 8 times 5 divided by 2 is going to be 20. And the unit that didn't cancel is pancakes. And there's our final answer. So with 8 eggs, based on the ratio that we had that was in the recipe, we could make 20 pancakes. Okay, a similar problem. It's just now we're moving on to chemistry from kitchen recipes. It says if we have 3 moles of N2 and more than enough H2, that just means that we have excess or we have extra laying around. So we have more than we need. It says how much NH3 can we make? So let's write down what we know. I know I have 3 moles of N2, and I'm wondering how much product can I make? So this is what we have, and this is what we want. And I'm going to set it up very similarly to what we just started with in the last problem. I'm going to have 3 moles, but instead of eggs, I have N2. I'm going to write a conversion factor. I'm going to cancel my N2s because that's what I'm starting with. I'm going to end with NH3 because that's what I'm looking for. And then my ratio is going to be 1 N2 for every 2 NH3s. And then I'm going to take this 3, multiply by 2, divide by the 1, and that gives me 6. And that is moles of NH3 because that's my unit that didn't cancel. So in other words, if I completely react 3 moles of N2, then based on this balanced reaction, I can make 6 moles of NH3. Okay, so to do any stoichiometry problem, I need moles and I need a balanced reaction. So I'm going to write a checklist up here, and we can use this to get started. So if I look at the reaction they gave me, this reaction is balanced. So I've got the same number of carbons, oxygens, and hydrogens on both sides. Although it doesn't give me moles. Instead of giving me moles, it gives me grams. It says I've got 5.0 times 10 to the 2 grams, which is really 500 grams of octane. So because it doesn't give me moles, I've got to take that grams and I've got to convert it to moles of octane. So my first step in this problem is going to be to convert grams to moles. But to do that, I've got to look up my value for carbon on the periodic table. So if I look up carbon, carbon is roughly 12. And if I look up hydrogen, hydrogen is roughly 1. If I look at the formula up here, I've got 8 carbons. So I'm going to take 8 times the mass of carbon. I'm going to add to that 18 times the mass of hydrogen, which is roughly 1. And 8 times 12 plus 18 times 1 is going to give me a molar mass of 114, and the units are grams per mole. Okay, that value is going to help me convert my 500 grams that I started with over to moles. So let's do that. I've got 500 grams of octane. And I'm going to take 114 grams for every 1 mole. And then 500 divided by 114. That works out to 4.386. And that's moles of octane. Okay, so now we've got moles. If we go back to our checklist at the top, we have moles. We had a balanced reaction. Now we can get to the stoichiometry. So I'm going to take that 4.386 moles of octane, and then we have to look at our balanced reaction. For every 2 octanes, we look at the coefficients, and let's see what the problem is asking for. It's asking for CO2, so I'm going to focus on the 16. I'm going to get 16 moles of CO2 for every 2 moles of octane, so that's my conversion factor. So I take 4.386 times my 16 divided by 2, and that works out to about 35.09 grams, or excuse me, that's moles, and that's of CO2. Now we're not quite done yet, because the problem asks not for moles of CO2, but for mass of CO2. So we've got to go that last step of taking moles to mass. So to do that, we've got to find the molar mass of CO2. So for carbon, if we look it up on the table, carbon is roughly 12. Oxygen is roughly 16. And in CO2, I've got 1 carbon and 2 oxygens. So I'm going to take 1 times the mass of carbon plus 2 times the mass of oxygen. So 1 times 12 plus 2 times 16 gives me about 44, and the units on that are grams per mole. So I'm going to take that 35.09 moles of CO2, and I'm going to use this molar mass to convert it back to grams. So I'm going to put moles on the bottom, and for every 1 mole, we just added up that I have 44 grams of CO2. So I'm going to take 35.09 times 44 divided by 1 is going to give me my final answer. And that works out to about 1,543.96, and that is grams of CO2. Or if we base this off of the original sig figs, that cuts it to about 1,500 grams CO2 if we express that in proper sig figs. Now we get a little bit more complicated by moving to limiting reactants. They don't just give us 1 value to start with anymore. We have 3 cups of flour, and for our eggs, we have 10 eggs, and for our baking powder, we have 4 teaspoons, and now we're asking how many pancakes we can make based on what we have on hand. So I'm going to do 3 different calculations. Based on the flour I have, I'm going to see how many pancakes I can make. Based on how many eggs I have, I'm going to repeat that calculation. And then based on the baking powder, I'm going to see again how many pancakes I can make. And then we'll learn how to look at those values and determine which one is going to be correct. So let's start with the flour. I've got 3 cups of flour. And if we look at the recipe, 1 cup of flour for every 5 pancakes. So I'm going to put 1 cup of flour at the bottom for every 5 pancakes. Cups are going to cancel. 3 times 5 divided by 1 that tells me I've got enough flour to make 15 pancakes. So now we've made our prediction based on flour, so we're going to move to eggs. So here I've got 10 eggs, and we're doing all of these like conversions. Only now it's a ratio of 2 eggs, and I'm putting eggs on the bottom so they cancel, for every 5 pancakes still. And 10 times 5 divided by 2 is going to be 25 pancakes. So let's pause for just a minute. Based on the amount of flour I had, it says I can make 15 pancakes. Based on the number of eggs I have, it says I could make 25 pancakes. So let's go on to the baking powder. Baking powder says I have, 4 teaspoons. And then the recipe says for every 0.5 or 1/2 teaspoon, I can make 5 pancakes. So I'm going to say 0.5 teaspoons of baking powder is going to give me 5 pancakes. So 4 times 5 is 20, and divide that by 0.5, and we get 40 pancakes. So which one of these is right? That's now our job. So let's think about this. Based on 3 pancakes, let me get a different color marker here. Based on 3 cups of flour, I could make 15 pancakes. In other words, I have enough flour to make 15 pancakes. I have enough eggs to make 25 pancakes. I have enough baking powder to make 40 pancakes. So if you think about that in terms of a recipe, I've only got enough flour to make the fewest pancakes. Only 15 pancakes can be made here, and that's because my flour runs out once I've made 15 pancakes. So we would say that flour is limiting. So I'm going to write limiting up here because it limits how much of my pancakes I can make. So we went through, we looked at each value predicted about product made, and we went this with the smallest value. In this case, it was only 15 pancakes, and that's because my flour would run out first. Now, we said that flour was limiting. Now, that meant that I had extra eggs, but in chemistry terms, we would call that excess. So I have excess or extra eggs. I would also have excess or extra baking powder. And that makes sense because for eggs, I had enough to make more pancakes. And for, baking powder, I had enough to make even 40 pancakes. But where did I have to stop making pancakes? Well, I had to stop at 15 because that's where I run out of flour. Okay, we've got another limiting reactant problem, and how do we recognize these? Well, because we're not giving one value to start with, we're given 2 values to start with. Now, it says what's the limiting reactant and what's the theoretical yield of TiCl4. So this, TiCl4, is what we want. And we have information on both of the reactants to start with. So let's rewrite this down here where we can work with it. So 2Cl2 is going to go to TiCl4. Okay. So the problem asks how much of that product is going to be made. It tells me that I have 1.8 moles of titanium, and I have 3.2 moles of Cl2. And I'm going to do a calculation for each of these, just like we did in the pancake problem. And I'm going to figure out how much TiCl4 we're going to make. So first, I'm going to work with the titanium, the 1.8 moles. So let's start there. 1.8 moles of titanium. Now, we're given moles. We're given a balanced reaction, so we can jump straight into the stoichiometry. I'm going to put moles of titanium on the bottom. I'm going to put our product that we're looking for on the top. And then I go to my coefficients. I've got coefficients of 1 for each of these. So for every 1 titanium, I get 1 TiCl4. 1.8 times 1 divided by 1. Well, that predicts I'm going to make 1.8 moles of product. If I repeat that with my 3.2 moles of Cl2, then I'm going to have a new ratio. I'm looking at 2 Cl2s for every 1 mole of product. I'm going to put Cl2s on the bottom. And then 3.2 times 1 divided by 2. That equals 1.6 moles of TiCl4. Now, we got a little curveball here. This is a term that says theoretical yield. So really, that's a fancy way of saying, theoretically, how much could I make? Or yield, how much could I produce? So that's the exact same thing we just did. It's just the verbiage, the language is a little more fancy. Okay, so looking at these two values, we pick the smaller amount of product that's predicted. So we would say that 1.6 moles of TiCl4 is produced or is made. That's another way of saying that's my theoretical yield. Now over here, the Cl2 is the reactant or the ingredient that predicted I would make less product. So we would call Cl2 our limiting reactant. And the problem doesn't ask for it, but titanium, well, titanium would be excess. And it's excess because it predicted the larger amount of product. All right, so here we're going to the most complicated limiting reactant problem that I could throw at you. We're going to throw in a concept called percent yield at the end. Now again, we notice this is a limiting reactant problem because they don't just give us one value, they give us two values to start with, and it's a prediction problem. It's saying how much product will be made. That's why we know it's stoichiometry. Okay, so I don't know about my sodium chloride, and they give me both of my reactants to start with. Now if I come over, I write my checklist. I need moles, and I need a balanced reaction to be able to do stoichiometry. They give me a balanced reaction. If I take a look here, I've got 2 sodiums on each side as long as I put a 2 in here. And I've got, let's see, with a 1 out front, I've got 2 chlorines on this side, 2 chlorines on this side. Now it's balanced. I need moles. They don't give me moles, they give me grams. So I need to convert to moles before I can start doing any stoichiometry. So I'm going to come in here and say 53.2 grams of sodium. If I look up sodium on the periodic table, for every 1 mole of sodium, I've got 22.99 grams. So 53.2 divided by 22.99. Let's see what that gives me. That gives me 2.314. And that is moles of Na. Let's do the same thing for Cl2. Now for Cl2, I start with 65.8 grams. And for Cl2, the molar mass, for 1 mole of it, if we add it up off the periodic table, it's going to be 2 times the value for chlorine, and that works out to 70.90 grams for every 1 mole. So 65.8 divided by 70.90. All right, that gives me 0.928 moles of Cl2. And all right, so let's go ahead and move on to our next step here. Now we're going to predict the amount of product based on these moles of Cl2 that I have. And we can do stoichiometry because now I have moles and I have my balanced reaction. We had to have both of those before we could start using the ratios and doing stoichiometry. So let's start with 2.314 moles of Na. And if I go to the balanced reaction, for every 2 moles of Na, I will make 2 moles of product. So I'm going to write that in here. So 2.314 times 2 divided by 2 is going to give me the same value I started with, 2.314, only now it's going to be moles of NaCl. Now next, I'm going to do the same thing but calculate it for Cl2. So I'm going to start with 0.928 moles of Cl2. Only now I look at the ratios for Cl2, which is 1 to 2. So for every 1 Cl2, I'm going to make 2 NaCls. These are from the coefficients in the balanced reaction. So 0.928 times 2 divided by 1, and I get 1.856, and that is moles of NaCl. So just like in the pancake problem, I have multiple values of this answer that I have. I'm going to pick the smaller of the two answers because that's the more conservative amount of product that's going to be made. And we would say that the reactant that we use to calculate that is the limiting reactant because it predicts the smaller of the two amounts predicted. So we're not done yet because this problem is going to want percent yield. And to get percent yield, I'm going to need to take this an extra step. Now, this calculation just said we could make 1.856 moles of product. That's another way of saying theoretically. But the problem also gives us an actual amount. Because it says that only 86.4 grams were actually collected. So when we carried out this reaction, we could have made 1.856 moles, but we only actually collected 86.4 grams. Now, to compare this actual value with this theoretical value, we do a percent yield calculation. So if I look at percent yield, it's going to be 100% multiplied by actual divided by theoretical. Now, these do have to speak the same language, so I'm going to have this in terms of grams because my actual yield is in terms of grams also. So let's go ahead and do that. So we are going to take that 1.856 moles of product that we predicted, and to be able to convert that between moles and grams, I'm going to need, in this case, molar mass of NaCl, and that's going to be the mass of a single Na and a single Cl off the table, and that amounts to 58.44, and that's grams per mole. So when I come up here, I'm going to put moles on the bottom. That way they'll cancel. Grams on the top, and for every 1 mole, I'm going to have 58.44 grams. So I'm going to take my 1.856 times my 58.44, and that'll give me my mass in grams of product. And that gives me 108 grams of product. Now, that's when I take into account my sig figs. It's 108.46 and change, but we started with 3 sig figs, so we're going to end with 3 sig figs here. Now, this is the amount of product that I would actually make, well, excuse me, theoretically make in grams, because this is purely calculation. In our previous slide, we calculated how much we could make, and that's important, because when we look at theoretical yield, this theoretical is could. The actual that goes on top, that would be what we did make. So could make versus did make. So when I go to calculate my percent yield, we just said we could have made 108 grams. We did make 86.4 grams given by the problem. We take all that, we multiply by 100%, and then we get our percent yield, which works out to about 80% yield, which means somewhere in the process we lost about 20% of what we could have made when this was carried out experimentally.